thanks a lot. Thanks to the organizer for giving me the opportunity to speak today, and also for organizing this very nice semester that I'm very happy to participate in. Okay, so today I would like to talk about joint work with Julian Fischer, my PhD advisor, and also will mention and invite other people that have been working on the topic. So, the plan of my talk is the following one. So first, I would like to briefly introduce the curvature flow and the Allen-Cahn phase field model as a phase field approximation for the reason by mean curvature flow. Then I will talk about the convergence of the Allen-Cahn equation towards mean curvature flow. The proof I will show you are additive in the sense that rates of convergence have been proved. And first, I will present the two-phase setting, because so I think it's very nice to present the two-phase setting because it motivates some of the idea behind the proof of the multiphase setting, but also somehow show already what are the main issues of the multiphase setting that have to be overcome. And then at the end, I will briefly mention some current and future working directions. Okay, let's start with mean curvature flow. Mean curvature flow is a geometric evolution equation for interfaces in multi-phase system that has been introduced by Mullins to model the evolution of grain boundaries in polycrystals. So first of all, I should say what I mean by phase. Okay, a phase would be like a certain orientation of the lattice in a material. So maybe I can make some maybe I will write something on the blackboard and everybody. So like for example, we have a material, then we have in some parts this orientation of the lattice. Region of the space, this one, and another region of the space. And then there are interfaces, let's say, here and here, where the orientation of the material changes. And these interfaces, the evolution is described by mean curvature flow that can be obtained as the radial flow of the interface area functional. So, because I'm going to talk about multiphase setting, what I have to say is that in the multiphase setting we have more than two phases. So, for example, at least three, as in this case. So, in order to describe the evolution of the we need a set of characteristic functions. Each of those is associated to one phase. So, let's say, for example, for this we have chi I. For this we can have alpha, and this would be alpha. That takes value 1 in the corresponding region. One of the main features, some of the features of mean curvature flow is the occurrence of topological changes and geometric singularities. For example, during the evolution, it might be that some interfaces get shorter and shorter, and then at some point they just disappear. And one example is, for example, the shrinking circle. So, like, I think it's one standard example of evolution by mean curvature flow. So maybe it should make it larger. So we have a circle that then starts shrinking, and then disappears at a singular time. This is what I mean by geometric singularities and topological change. And this is one of the main examples. But also, in the multiphase setting, I have to mention that something that characterizes mean curvature flow are triple junctions. What I mean by triple junctions is the point where three interfaces meet. And these triple junctions, that could be, for example, this one here. Okay, this is the interface. Okay, we make it like this. We make it like this. Okay, there are some angles at which the interfaces meet that depend on the surface tensions. So different surface tensions give different angles. And then when we assume that the surface tensions are the same, we have triple junction meeting at 120 degrees. Okay. So, due to the occurrence of these topological change, geometric singularities, and also these points where interfaces meet together, sometimes it's easier to approximate mean curvature flow, the evolution by mean curvature flow, by means of a phase field model. What's the main idea behind a phase field model is that of replacing sharp interfaces by diffuse transition layers. So basically, instead of having a characteristic function that takes value 0, 1, in some region of the space now, writing some representative one-dimensional case, okay? Instead of taking characteristic function taking value 1 and 0, so these characteristic functions are replaced by some diffuse transition layers, so by some, for example, in the two-phase setting, by a scalar u, an ordered parameter, that can take value between 1 and 0. So that, instead of having a sharp interface, one has a diffuse transition of a width of order epsilon. And this is what happens, and as you can see here, somehow the phases are allowed to mix together in this region of the space of width epsilon. In the multiphase setting, okay, u, the order parameter, is not a scalar, that is a vector, and can take value along the path connecting the alpha. What are the alpha? Are the full phase states. So each alpha corresponds to a full phase. So instead of having 0 and 1, for example, we have, in the scalar case, so the two-phase case, we have some vectors. Okay. So the Allen-Cahn equation can be obtained as the gradient flow of the Gibbs-Bourbon energy, which is the following one. So we can see the parameter epsilon. Then we have some where we have a potential W in the multiphase case, that it's a multi-well potential with 0, of course, in the alphas. So the zeros, the minima, are at the full phase state. So these states are the most convenient energetically. So here, for example, I represented multi-well potential in the case n equals 3. So we have 3 phases. It's quite symmetric because we have that the minima are at the vertices of an equilateral triangle. Then we have a bump in the interior, and then we have some quadratic growth along these sides connecting the minima. Somehow this could be some generalization of the two-phase case. I think that most of you are familiar with the standard double well potential like this. So in this case, if you want to be consistent, the 0 between 0 and 1. 0, 1, 1. And yeah, I will kindly ask you to keep in mind this picture because it's the kind of potential I will be working with. So, okay, and then the Allen-Cahn equation is obtained as the true gradient flow of this energy properly accelerated by epsilon. And that's what we get. So we have a diffusive term, and then we have the gradient of the multi-well potential with respect to u. Because here we have two spaces. We have RD, that is we have like it's the space where our material lives. So we have different phases, and then we have this Rn minus 1, that is where u takes value. Okay. Now the question is, okay, we have introduced the Allen-Cahn phase field model as an approximation of mean curvature flow when this epsilon goes to 0, and then the question is, does the Allen-Cahn equation converge to multiphase mean curvature flow if we let epsilon go into 0? So do we recover the evolution of branch interfaces by mean curvature flow? And the answer is yes. There are several results in this sense that I would like to mention. So in the two-phase case, so mu is a scalar, when we work with the standard two-well potential. So this obtained has been obtained in a quantitative way, so obtaining also the optimal rate of convergence epsilon, by means of asymptotic expansions first, and more recently by means of the so-called relative energy method that we are going to talk about in a few slides. As for the multiphase case, so when n is larger than 2, 3 for example, there are only some formal expansion. There is only some formal expansion analysis, and there is a qualitative conditional convergence result that basically assuming that the totally energy converges in the L1 norm in time, one can recover BV solution to mean curvature flow as a limit. But this is conditional because there's this assumption on the convergence of the energies, and and also it's qualitative. Doesn't provide any rate of convergence. So what's the main challenge, let's say, in obtaining a qualitative result, not conditional? It's let's say the occurrence of these triple junctions. So when that occurs in the multiphase case, for example, when n is 3, that by means of asymptotic expansion, so far people have not been able to create. Together with Julian Fischer, my PhD advisor, we have been able to prove quantitative unconditional convergence for a class of potential like the one that we have seen in the picture before, just to have something in mind, and by means of this so-called relative energy method that I'm going to talk about in the next slides. So, what our result says is like when you are in the 2- and 3-dimensional space and we have more than 3 phases, assume that we have a partition of the space whose interfaces smoothly evolved by mean curvature flow, and whose interface is eventually meet at triple functions of 120 degrees, which means that we are assuming same surface tensions. Then assume that we have U, a bounded weak solution to the vectorial Allen-Cahn with a multi-well potential that belongs to a suitable class of potentials, like for example this one in the picture. Then assume that we can have some approximate phase indicator function psi, then we can get our result. So first I should say what are these psi. These psi have to be constructed. So given the multi-well potential, we have to be able to construct them because their role is that of approximating the partition once we compose them with U. So basically, as our result states, it's that for well-prepared initial data, so some initial data that are already approximating the initial data for the partition, then we can get an error estimate in terms of the L1 norm of the difference of this psi I composed with U and the chi I. So basically, psi I. So basically, when U, for example, takes value alpha I, then I expect this psi I composed with alpha I to be equal to 1 because it's approximating the characteristic function chi I. When U takes value, let's say, alpha j, with j different from I expect psi I composed with alpha j to be equal to 0. And that's the idea behind the construction of the psi that I'm going to show you later. So what I have to say, okay, our error estimate gives a rate of convergence, which is epsilon to the power of 1/2. We obtain this rate of convergence that, as you can see, is somehow suggesting us that it's not the optimal one, because the optimal one should be epsilon, because it's the error estimate that we can obtain by using our relative energy functional. So you see the role of this functional, and it seems that in order to improve the rate of convergence that we can get, we should slightly modify it. Okay, but for the moment, this is what we are able to get. Okay, in the next slide, I would like to show you the methods. So first, I would like to introduce to you the relative energy method that I've already mentioned a few times. So what's the general idea behind that? And then to show how we can use it in the two-phase case, and then how we can try to generalize the ideas to the multi-phase case, and what are the issues that we encounter. Okay, the relative energy method, more in general, is an idea that originates in the work of Fermat and Berna, and the idea is that of having a functional, a nonlinear functional, that is able to measure the error between two solutions. So it can be used to prove Weak-strong uniqueness when we want to measure the error between two different notions of solution, one weaker, one stronger. But it can also be used in our context, in which we are measuring the error between a solution to a sharp interface model and a diffuse interface model. Well, the idea is like having a definition, having an answer for a relative energy. We try to prove coercivity properties for this functional so that we can get a relative energy inequality, and then by means of a Gromwald type argument, having this kind of bound also for the initial data, so that the initial solutions are not so far away from each other, we can get the same bound at any time. So, example application of this method, okay, has been used in the context of mean curvature flow by my PhD advisor and collaborators to prove Weak-strong uniqueness of V solution to multiphase mean curvature flow, and then also to prove quantitative convergence of the Allen-Cahn field model towards mean curvature flow in the two-phase setting and in the multiphase setting. Okay, so a few words regarding these results in the context of Weak-strong uniqueness of V solution. Okay, this work, it's in the two-dimensional space. So when three functions are in the d is equal to 2, and we are in the two-dimensional space. And then there's this other work by in which they study the case of they prove the result in the three-dimensional space. So when d is equal to 3, and then instead of treating triple junction, they are able to treat triple line of the type of double bubbles that we see. Why I'm mentioning this result? Because as you will see, we are using some tools. Okay, so first of all, now I would like to show you how we exploit this method. So having a relative energy, being able to prove coercivity properties so that we can get a relative energy inequality, and then the Gromwald type argument in order to conclude, to prove quantitative conversion of the Allen-Cahn equation in the two-phase setting. So let's start for the two-phase setting. So when n is equal to 2, u is a scalar, and we have the standard true-well potential like that. Okay, what's a good answer for the relative energy is the following one. I think that we already know this for two terms, as it begins with an energy from which we can get the Allen-Cahn equation of L2 gradient flow, but then we have this additional term here. Okay, now the question is, why does the relative energy have this form? And also, what is this psi? First of all, this will be psi. And then the second question is, what about the psi? Okay, so psi is nothing but an extension of the unit normal vector field unit normal vector fields of the interface, the sharp interface evolving by mean curvature flow. So how can we construct it in the two-phase case? Okay, so when we are along the interface, we just take the normal vector field itself. When we are away from the interface, what do? Okay, for example, if we are here, we project this point onto the interface, we take the normal there, and then we multiply by the cutoff function so that when we go away from the interface, it just gets shorter. And then specifically in a quadratic. Okay, then what is the psi? The psi, we define the psi in this way. So as the integral of the square root of the 2w. Okay, then we go on, and then we see if by defining the psi like this, we can get some good coercivity properties for this definition. People that are familiar with the modified molecular result, it's suggested by that result also. Why? Okay, so and in this relative energy we can first have some nice coercivity properties. So what do we do? Okay, this is just the density of our relative energy, this term and this term. Okay, we add and subtract this term, which is nothing but the gradient of the approximate phase indicator function. As you can see. Then we notice that this one, of course, is larger than 0, as it's just a square. And then we notice that this one is the gradient of the psi. So we can substitute this with the gradient of the psi. Okay, now here we have this gradient, here we have this gradient as well with the scalar product. So we can rewrite this term in this way. So we just take this out. Okay, but then we have this. This is larger, let's say, than this. Because we have this length property for the psi here, that it gets shorter going away from the interface, so it's less than 1. And then we have, okay, what it's telling us somehow is that we are able to control, so our relative energy is able to control the error somehow between this psi, that is nothing but an extension of the unit normal vector field, and what is this one? It's the phase field counterpart of the normal. Because I should remember that psi composed with u should approximate the characteristic function in both. Okay, so this is a nice coercivity property that one can exploit, and there are some others, in order to prove a relative energy in type of inequality, and then, okay, so that by a ground type argument we can get this inequality, and then by means of some technical work, one can obtain the bound in L1 norm. What I would just like to observe is that if we get epsilon squared here, then one will get epsilon here. So he suggests us that if I'm getting epsilon to the power of 1/2 here, in the multiphase case, it means that here I can only get epsilon. Okay, so now let's have a look at the multiphase case and what are the troubles in that case. So I already mentioned that one issue is the triple junction, and it might be because so we have an extension of the normal vector field here. So how do we extend close to the triple junction? That could be a point, and then the second point would be, okay, but if u is the vector, and then we have a multiple potential, how do we extend this definition in the multiple setting? Okay, let's have a look at the multiphase case. So, okay, the first two terms of the relative energy can be actually the same ones, also in the vectorial setting. Then, a nice idea could be that of adding a sum here in front of this last term. And then we can put an I in for the psi and the psi. So we have one for, let's say, each phase. Okay, but now the question is, what are the psi and what are the psi? So, okay, the psi are provided by these two words. By the first one for triple junction and by the second one for double bubbles. When we are in the two-dimensional space or in the three-dimensional space. So it's not trivial to construct these extensions because we need some good properties at the triple junction, for example. Especially we need some compatibility condition of first order up to the first order, so also for the gradients. And due to this regularity that we need, the construction is not trivial at all, and can be found in these two works, that it's easier also to prove its strong uniqueness. Okay, what are the main properties of this psi? Is that when we take the difference between psi I and psi j, and we define this psi ij, then this coincides with the normal to the interface iij. That, for example, here it's iij. And then, also in this case, we have some growth. Okay, so now the remaining question is, what are the psi? Okay, the psi, the construction of the psi is not trivial. And they have to be constructed as in the two-phase case by means in terms of the W, in order to get coercivity properties of E, so that we can do, let's say, the same argument once we have the same bound for the initial data. And as I said before, for us k is equal 1, so we don't get the optimal rate of conversion, but we get 1/2. This is due to the structure of our relative energy answer as 1 when one tries to approximate the partition just by the initial partition, just by somehow extending the idea of the optimal profile of the two-phase case. Anyhow, I should tell you something about diffuse size, because diffuse size play a huge role in the sense that once are composed with U, they should approximate the phi. Okay. So this is our aim now, and I'm going to show you this in the three-phase case, as it's easier to show because in the three-phase case we kind of have an idea of how the potential might look like, because I can represent it as having the minima at the vertices of an equilateral triangle, let's say, so we can have a picture in mind. Okay, so as I said, in the n equal 3 case, so the minimum of the potential are at the vertices of an equilateral triangle. Yeah, okay, here we are. This is our potential. I just represented this triangle here again, and then we have the minima alpha 1, alpha 2, alpha 3. The full case are the minimum. Then the 0, so are the vertices. Then we can assume, for example, that so basically the minimizing path along the potential correspond actually to these to the sides of the triangle. So it's more convenient to move to go, for example, from alpha 1 to alpha 2 along here. That correspond to the side. And then we can assume, for example, that W along the side of the triangle, it's like behaves like a standard W potential. And then we assume some regularity property of W, especially that is symmetric with respect to the medians. So there are some huge coercive. We have some symmetric properties. And then we assume that there's a large bump in the interior. Why all these assumptions? Because what would be nice to do is somehow to try to exploit what we have in the two-phase case, somehow try to reduce to the two-phase case as much as we can. And that's why this motivates why we have a large bump in the interior. Because there's a large bump in the interior, energetically it's more convenient to move close to the side, so somehow it's more convenient to be close to the two-phase case. This is one motivation for this, and then of course, standard double well potential along the side, somehow we can use what we already have. Okay, but then having these nice properties, how still can we define their size? Okay, as I said before, it's reasonable to set that psi I equal to 1 at the alpha I. Then it's reasonable to impose that they are smaller than 1 when u is different from alpha I. And that, for example, psi k, which is the approximate function corresponding to the phase k, is equal to 0 in this subtriangle. So basically, when we are in this yellow triangle here, so basically psi k takes value 0. So we have only to work with the phase 1 and 2, and not with the phase 3. Then along the side, so along, for example, this orange side of the triangle, we define psi I u as 1 minus the geodesic distance of u to alpha I. But the geodesic distance, I define it also here, is just the income along the C1 path connecting u to alpha I. And then, of course, we have to extend this definition in the interior of the triangle, because so far I've given the definition only only along the sides. What we want, or what we are trying to achieve by constructing this size, is to have that psi j minus psi I, this sign is just convention, let's say, such that when we take its absolute value, its length, the gradient of psi u with respect to u is smaller than, especially smaller than square root of 2w. Somehow this, because if we remember the two-phase case, we had that gradient of psi u was exactly equal to the square root of 2w u square root of u, gradient of u. So somehow this is the generalization of this property in the multiphase case. But in the multiphase case, actually we want something stronger, as we will see. And so the construction cannot be needed. Okay, now let's have a look how we can exploit this property. Okay, I recall my definition, my answer for the relative energy. I recall that these psi ij are nothing but some extension of the normal vector field to the interface ij. Then we want, our definition of psi ij, or our construction of psi ij should give this property. Because then, when we are, for example, in this yellow triangle, or any triangle ij, what we can do is the following. Okay, we can do as before, adding and subtracting this blue term, first of all, to the density of our relative energy. Then we know that this one is larger than 0. And then we have this left term here. What we can do again, of course, now we have a sum here. We have a sum here that even though now we write everything in terms of psi ij and psi ij by using the sum and the difference, then there are going to be some missing terms here. So that's why I need something stronger here. And then we're going to have something like this that again can give us, as in the two-phase case, can tell us that our relative energy is able to control in this, let's say, triangle that corresponds, the error between the extended normal vector field ij and its ij counterpart given by the phase field model. So somehow what I wanted to tell you is that what we have in the two-phase case can be recovered in the multi-phase case by means of a lot of technical work, but that requires some stronger conditions. And for this reason, we are only able to treat only a class of potentials, because still our strategy requires the fact that we want to try to reduce as much as possible to the two-phase case, which is a way much simpler. Yeah, so, but at the end, somehow one can manage to get these nice coercivity properties that tell us that our relative energy answer is reasonable, it's doing the work that we want it to do, so it's able to control the error between these two normal vector fields, this real normal vector field and this approximate normal vector field, at least in this region. Okay, when u takes value in the triangle tau ij. So for each of these triangle, for example, in the triangle yellow, we have a control of these in terms of the 1, 2 of the corresponding quantities for the cases 1. Okay, and these coercivity properties, together with some other ones, let us get the relative energy inequality that we've seen before, and so conclude our argument and get our rate of convergence. Okay. What? Oh, so we have this. We have this. Then, thanks to this and other coercivity properties, we can get the relative energy inequality, and then we can conclude our argument and get the final rate that we were looking for. Okay, so what are the achievements by means of this relative energy method? Okay, we have the proof for the two-phase case. We have the proof for the multi-phase case when we are treating triple junctions and for the case of double bubbles. But what we would like to have a look at is also, we would like to prove our result also for a wider class of potential, because as I've shown you, there are some restrictions on the class of potential that we can treat. For example, it would be nice to try to treat the Mexican act. One potential that doesn't treat this. And then, of course, one could have a look at the general surface tensions. So when the two equal junctions meet at angles that are different from 120 degrees, okay, that should be doable, as the construction for the gradient for calibration, also for these extensions of the normal vector fields, is provided for general surface tensions. So this means that there's going to be some more computations to do, but it should be still doable. Okay, what's next now? Okay, when I talk about link-over flow, I mentioned that link-over flow features the current of topology change and singularities. And especially I mentioned the shrinking circle. So the circle just disappear. Our result, the Wickstrom uniqueness result that Julian and collaborators have been able to prove for these link-over flow, hold only prior to the first topology change. So we are not able to treat yet a shrinking circle, for example, because it's a singular time, or some other singularities of interpretation. For example, the shrinking circle. And then there are other stable shrinker, asymptotically stable shrinker, that are like the lens, the X-ray star, the X-ray star, and also like the standard cross. So this happens basically when two triple junction collides, and then usually they collide and then also they go. So there are two phases. So basically first they collide and then they go away from each other. So these singularities, these stable shrinkers, it would be interesting to treat these stable shrinkers. And actually this is what we have been working on recently. In particular, at the moment, we are working on the shrinking circle, as it should be the simplest, let's say, to treat. And first, we are trying to prove Wickstrom uniqueness in the case of the shrinking circle, let's say. And then, of course, once we are able to prove Wickstrom uniqueness, as we need a good notion of gradient flow calibration, so this normal extension of the normal vector field to the circle in this case, then once we have this tool, then we should be able to prove also quantitative conversion of the vectorial Allen-Cahn equation toward multiple phase link-over flow beyond dynamically stable singularities as first for the shrinking circle. Okay, then one now may object that the normal to the shrinking circle is trivial to see and should be trivial to extend. Actually, not really, because we have to modify the standard construction, because otherwise we are not able to compare two different notions of solution. For example, when we are far away from the singular time, it doesn't matter if we are comparing two shrinking circles that are, let's say, one here and one here. But if you are going to the singular time, then this time lapse counts. So the construction is not trivial anymore. Same applies if the circle, for example, are not centered at the same point. We still can compare them, but they are not centered at the same point, and then when they shrink and we want to go beyond singular times, then this counts. Okay. And that's it. Yeah, there are a couple of references, the two-phase setting and the multi-phase setting, and hopefully some others. Thanks a lot for the attention.